Well, the next two things I'm going to tell you, we will make up little problems about for this class, but really they're critical to understand for 126. So you're all taking 126. Who in here is not taking 126? Admit it. Oh my God. Why on earth would you only take 125? This is the boring one. 126 is the exciting one. I don't know what these PAAs are telling people. I don't know. So let's say real waves are in between. There is no wave that is a perfect plane wave. A perfect plane wave has infinite energy because it has a constant amplitude over an infinite plane, and there's no wave with infinite energy. There's also pretty much no perfect spherical wave. Nothing is perfectly spherically symmetric like that. Why is the amp decreasing? To conserve energy. So it's beyond what we could say now, but when we get into amplitudes Tuesday, we could talk about it. But the energy in this wave is basically the amplitude times the area, the surface area of that sphere. So as this thing moves out, that surface area gets bigger. And then the energy then of the wave of each wavefront would be increasing as it gets bigger. So the only way you can conserve energy is as the area of the wavefront gets bigger, the amplitude has to get smaller. That's the short version of the answer. So we'll address it a little bit, I think, Tuesday when we do intensities. I'm making this up as I go along. Okay. Do I really look like a guy with a plan? No, I don't think I do. Is the final cumulative? No. Or yes, we haven't decided. Do I look like a guy with a plan? No. We don't know. Okay, so real waves are in between. So let's have, Kesha's back. I'm going to get sued by Kesha. Spider eye. Okay. So what does the thing coming out really look like? Like when I'm talking at you, it's not a plane wave. If it were a plane wave, just a piece of a plane wave, only like you would hear me, right? And it wouldn't go anywhere else. It's clearly going out like this. But it's not quite a spherical wave, because if I get this way, you can't really hear me anymore. See how much louder it is when I'm this way, and then when I'm this way, you can hardly hear, right? That's because it's not really going behind me as much. It's kind of barely going behind me. So really, if we had to plot it, it's sort of like a cone wave. It's like sort of a piece of spherical. Now in homework, we'll say assume it's a spherical wave or something, but there's a reason I'm showing you this. So you would say right along this line from Kesha's mouth to my ear in the front row, right? Looks something like that, okay? So we've got a thing, and it's technically the amplitude. Well, I don't know what's going on, sorry. Anyway, a wave goes that way, right? And then you get some going this way, but not as strong, right? Some going this way, but not as strong, like that. And then really weak that way, and really weak that way. Now you still hear somebody behind, because it's bouncing off walls and all kinds of, echoes are everywhere. Okay, so you could think of it as kind of a partial spherical wave. Okay. But what I want you to see is we could draw sort of what's called the wavefront curvature, like this. It's sort of saying, let's draw all of the amplitude maxima and draw a line connecting them all. Right? So there's the maxima. I didn't draw these to have a nice, even, uniform, whatever, sorry. But there's the minima. Right? So you get the idea. So what is this curvature doing as I get farther and farther away? Right? It looks like a plane wave. Right? So far away, spherical looks like plane. And we use this all the time in the kind of problems you're going to do next semester. This conversion from spherical to plane. Okay? Now that kind of sounds like a convenient thing to say. Is there any math behind this? Am I making this up? Sort of the math is you keep up with this radius of curvature, which is really just how far away you are. And what really matters? If my ear were really big, like bigger than it is, right, eventually this thing would curve. But all that really matters is your ear canal. I had to look up what to call that. I was like, what do you call the hole in your ear? I wanted to say something classy. Ear canal, okay? So as long as the ear canal, which is a few millimeters, is small compared to the distance to Kesha, which is like meters, tens of meters, couldn't afford the tickets, right? Then it's going to be a plane wave because it's going to have no curvature. But then another thing matters is that the intensity is dropping off as you go farther away, right? So you also need the extent, the length of your ear canal to be short compared to the length scale over which it drops off, which is related to the wavelength, right? So wavelengths of typical audio frequencies are sort of, meters, on the order of meters. So your teeny little ear canal doesn't care. Right? So for sound waves, your ear cannot possibly hear anything other than a plane wave. It thinks everything is a plane wave. Right? The plane wave hits your ear, and then all the magic happens inside your ear. Okay? Let's see. Latest questions. More phase to talk about. One's about E field. I don't want to go that far back. Ask me after class about the E field. Okay, so one thing I want you to be able to think about is you move far enough away from a spherical wave, it becomes a plane wave.